Hello and welcome to Lecture 7 of Chemistry for the Interdisciplinary Sciences. Today we're going to look at the combination of those two different bonding modes that we talked about so far, ionic and covalent. And we're going to talk about the hydrogen atom, which I mentioned was able to flip between the two. So today we're going to see how it's done. So let's glance at the learning outcomes. We're going to want to, by the end of this, define the term acid as in terms of donating protons and bases as acceptors of protons. We're going to have to name some common acids, and understand the pH scale as a whole. I'd like you to understand that there are some bases that can accept protons that are not alkalis, and we'll talk about that. And also understand the method of titration as a method of determining the concentration of a solution. So you're most likely to have come across the term acidic when it comes to things like food and drink. So orange juice is the quintessential acidic drink. If you're a wine taster, you might say zippy. Something tastes zippy. That is usually to do with the acidity inside there. But then something like my absolute favourite Pepsi, that contains phosphoric acid in there in order to basically prohibit bacteria from growing. So acidity then is that sort of zippy taste in there, and it's all to do with the protons. Water we define as being neutral, but it is in fact slightly acidic or slightly basic if you want to think about it that way. There are protons in there, and we'll talk about that as being our middle neutral ground. And then you might be aware of something like milk. So if you've got acid reflux or something like that, you might drink a glass of milk to try and reduce the pH in your stomach. Actually, it has more benefit in that it puts a bit of fat around the lining and stops the irritation of the cells. But anyway, you might think of milk as being mildly alkaline. Now, milk, when it goes off, transitions from alkaline to acidic as bacteria inside the milk respire the lactose, the sugar in there, over to lactic acid, and that is what makes milk go off. Whereas orange juice takes much, much more time to go off. And that's because it's already quite an acidic, unreasonable environment for bacteria to grow in. So what do I mean by those terms? Well, an acid is a source of protons. Now, I mentioned that this lecture was about hydrogen flipping between those covalent modes and those ionic modes, and that's exactly what it's all about. Remember, hydrogen only has one electron, its outer shell, so it can accept electrons and bond covalently, or it can give up those electrons and hang out on its own as just a proton floating about. That is this H plus business. The H plus is what I mean by proton today. So when I say it's a proton donor, I mean it gives out H plus ions. There. So an acid is something that gives up H plus ions, and a base is something that can take H plus ions away, that can accept it onto its own structure, make a new molecule. Quite often, that is going to be a source of OH minus ions, and we call those alkalis. So those are things that are soluble in water. That would be a soluble base. There. So let's have a quick glance. Here are some really common acids that you might have seen. Now, notice that the top three are acids of the common ions that we had to learn. And so again, it's worth just being aware of what's happening when it comes to those ions. We've got this chloride ion, when it gets a hydrogen involved, becomes hydrochloric acid. The sulfate ion, when it adds hydrogens, remember sulfate, SO4 2-, we need two H pluses then to equalize the charge. And remember, this goes back to the same as the sodium oxide example we did before, where you're looking at the same number of positives and negatives to cancel out. So when you get the acid of the sulfate ion, that's sulfuric acid. The acid of the nitrate ion is nitric acid. Again, NO3-, just the 1- means we only need one H. And then something like ethanoic acid or vinegar is also something that you're going to be aware of. Now, how are these acids? Well, in solution, the hydrogen doesn't really care about being covalent anymore. It will just give its electrons up and go off on its own as a H+. Now, obviously, the ability of the hydrogen to do that depends basically on how willing the other atom is to take the electrons onto itself. So something like hydrochloric acid and nitric and sulfuric acids, these are all really strong acids because the partners that the hydrogens are attached to are all willing to accept electrons. They're non-metals, they want to do that anyway, and they're also electronegative, which is a term I'm going to define later on. So these are all proton donors then. They can create H plus ions in various abundances there. And so that's what defines them as an acid. A compound that contains a hydrogen that can leave as an OH minus. On the flip side, some examples of bases are basically any old S block metal with an OH on it, with the right number of OHs on it. So we've got sodium hydroxide there, OH minus, Na plus. We only need a 1:1 ratio. Calcium hydroxide, calcium is in group 2 at the periodic table. So it's there in the 4s2 position, proton number 20. So it can give up 2 electrons. It will have to be a 2+ ion, so we need 2 OH minuses to cancel it out. And then ammonia is our other example that I'm going to show you later on. When these compounds dissolve in water, they make OH minus ions, and then OH minus ions act as proton acceptors, basically by grabbing hold, using its negative charge, grabbing hold of that hydrogen and making water again, all on its own. So an acid is something that will make those H pluses, a base is something that will take H pluses out of a solution. And so the acids are proton donors and bases are proton acceptors in there. So we can measure how strongly acidic or how strongly basic all of these compounds are using something called the pH scale. And here it is. We use water in the middle as our neutral, as our midpoint, and that is a pH of 7. Now you might wonder, why? Why 7? Why is 7 the number? The pH scale tells us exactly what the concentration of H plus ions is in solution in a unit called moles per decimeter squared that we haven't got to, moles per decimeter cubed that we haven't got to yet. So water has a concentration of H plus ions, and I'm just going to write this square bracket is a shortcut for concentration of. Of that in water is 1 times 10 to the minus 7 moles per decimeter cubed. I don't know why it does that. Again, we'll define those units even more as we go along. So 1 times 10 to the minus 7 moles per decimeter cubed there. If something has more acid in it, i.e. 1 times 10 to the minus 6, 1 times 10 to the minus 3, or even just 1 times 10 moles per decimeter cubed, then it's getting more and more acidic. So this minus 7 is what is related to this 7 here. Equally, if we get less and less concentration, times 10 to the minus 14 is a much smaller number than times 10 to the minus 7, then we have less and less acid, or more and more base, you might say. So over here, it's 1 times 10 to the minus 14. I'm going to use a big capital M, which means the same as moles per decimeter cubed, but be aware that really you should write moles per decimeter cubed. And over here, we're talking about 1 times 10 to the 0 moles per decimeter cubed there. So that's what this is. Each change in pH by 1 unit represents a 10-fold increase in concentration of protons, i.e. there are 10 times as many protons in a pH solution of 6 than 7, and 10 times as much on the next, and so on. So the pH scale is what we call logarithmic. It increases by order of magnitude every single time. What about the pH? pH stands for pouvoir hydrogen, i.e. the power of hydrogen or the strength of hydrogen there. So the pH is always basically just a representation of the concentration of H plus ions. And this scale here represents a series of dyes that chemists have put together called universal indicator that basically can tell you what strength of acid you've got just by looking at the colour itself. Now, the best representation of this is a demonstration called the rainbow tube, but unfortunately no one's recorded it in a way that looks great. So let's just very quickly look at what it looks like when you have a beaker of, in this case, very basic solution. You see how it's quite purple. Again, sorry if you can't see it, I will tell you that it's purple at the bottom, and the solution that we're adding at the top makes the solution very red. That suggests that we've got a base in the beaker, and we're adding acid to the top. And as it stirs in, the acid and the base are reacting, so overall it returns to an even pH. But as you add the acid at the top, the concentration of H plus ions at the top is slightly more than at the bottom. Now you can start to see that at the top we're starting to see some sort of green colours appearing. That suggests that the amount of acid and base that have gone in are becoming approximately equal. So right now it's yellow and green at the top and then purple at the bottom. It's getting more blue at the top. This means we're getting really close to balancing those two concentrations, and this is going to be the basis of something called titration that we look at later on. But you can see how really nice it is. Now what's happening to the dye, the way that the dye works is, the dye is itself an acid. So it has the ability to donate protons, but that means it must also have the ability to accept them back. And it's sort of in the middle here. At the moment what we're seeing is red at the top, yellow in the middle and green at the bottom. So now this solution is more acidic than it is basic anymore. It's got more protons floating about than normal water does. And so it is acidic. The dye, because of the large concentration of H plus ions around it, have accepted the protons onto themselves, and that's changed the structure such that it changes the colour. Now let's try and have a very quick look at the rainbow tube. So the rainbow tube is basically water with universal indicator in it. That's the mixture of dyes, and at the moment it's green. But what you do is you pop a pellet of sodium hydroxide on one side, and now what this person is doing is opening the other side and adding a drop of acid to the other end. I'm sure he's telling us that what he's about to do, so I'll just skip ahead. Yep, and in it goes, because you can see how red it is. And then the idea is that you hold the tube horizontally and you just let one diffuse into the other. And what we should see is that it's really basic on that side and really acidic on the other. And in the middle, we have all the possible transitions, all the other possible concentrations of H plus ions. So I'm not sure if you can perfectly see it, but for those who can't see colour, red, yellow, green, and then it's sort of blue-purple all the way across the rest of the tube there. But that's happening because the H plus ions are slowly diffusing over to the alkali on the other side, and therefore increasing the concentration of H plus up to normal water. And then after that, the base is pulling protons out of solution such that the concentration of H plus ions is less than normal water on the other side. And again, that's how we define neutral. Normally, water will separate into H plus and OH minus ions, like the slide we saw before, like this. So we're thinking about the arrow going in the other direction as well here. Water molecules split apart, and they do make H plus ions in a concentration normally of 1 × 10⁻⁷ moles per decimeter cubed. So there we go. If something has a low pH, that means it's 10 to the minus a small number in concentration, i.e. it has more protons, H plus ions, than normal water. Neutral, the water is at its normal dissociation value. Dissociation is splitting apart. And basic means it's fewer protons than water, i.e. something is removing them from the normal water solution itself. Now, what's not the case usually, and we already talked about this when we were talking about ions, there is no such thing as a source of H plus ions and a source of OH minus ions all on their own. Whenever you have an ion, it has to come with a counter ion. And so if I'm mixing together an acid and a base, what I'm going to get is water, just like on the last slide, OH and on the slide before, H plus and OH minus are going to react together to make that water. But also what I'm going to see is whatever the spectator ions are, the counter ions to the acid. So earlier on we saw sulfuric acid, hydrochloric acid and nitric acid. There we've got the sulfate, the nitrate and the chloride ions floating about. And when it came to the bases, let's just pop back and look at those. So there we go. That's the chloride, the sulfate, and the nitrate ion. And over here, what counter ions have we got to the OH minus ions? We've got the sodium ion and the calcium ion there. So when you mix together an acid and a base, you're usually bringing along some counter ion. So in this case, look, I've got the chloride ion is the counter ion to the H plus, and the sodium is the counter ion to the OH, which means that I'm going to make water when the H and the OH come together, and what's left over is a solution of salt. A salt is a combination of a positive and a negative ion. So remember again, like the ionic salt that we saw before, like rock salt, currently that salt is actually structural, like this salt here. Sorry, it's currently holding up a light. So let's have another quick look then at these examples. If we had sulfuric acid be the the acid that we're adding, then we expect to make a salt that contains that ion. So for sulfuric acid, it's sulfate, it will make something sulfate. Hydrochloric acid will make something chloride. Nitric acid will make something nitrate. And the same for the bases. If we've got sodium hydroxide, then we're going to make some sodium something, or calcium something. And ammonia will make ammonium, just FYI. So there we go. We expect our acids and bases to react together. We're going to make that salt and water. Salt is a compound made up of ions, and basically it's going to be whatever ion is left over from the counter ions. So if the pH scale here is telling us about the concentration of H plus ions, then if I wanted to find out about the concentration of an unknown solution, so let's say I had an acid and I have no idea how strong it is, what I can do is use the universal indicator scale to basically add a base until it goes back to neutral, because that is the normal concentration of H plus ions. So basically I'm adding something to remove H pluses all the way, and then I'll be able to tell when it's finished because it'll go to neutral. So you can imagine if I had a solution of universal indicator and hydrochloric acid or sulfuric acid, that would be a red solution. Of just the pure bases, they would be purple. And once it's finally got to its neutral point, whatever that is, we would get a green solution. And this is the basis of titration. The idea is that we would, I'll move myself over here, that we would basically add acid. So up there I've got acid because it's red. And at the bottom in the flask, I've got my base of some form. And what I need to do is I need to know the volume of the solution here. And at the top, I need to know the concentration and volume of that solution so that as it gets added in, so let's watch the animation if I can make it do it. Oh, apparently I can't. Yes, there we go. The acid gets added in, and we're going to stop adding acid when the solution goes green. So let's just watch that one more time. At the bottom, we're adding the base, the acid to the base until it goes neutral, and we'll stop there at that point. We'll know what that concentration is and the volume because we're going to use a piece of apparatus called a burette. So that's what we've got there. This is the burette. I'll write that on there just in case. It's basically just a tube with markings on it, almost like a measuring cylinder with a tap on the bottom. And the aim is you basically watch really carefully as you add your acid to your base until the substance at the bottom becomes neutral. When that happens, you can calculate the number of ions that you have in each case using the mole calculations in there. So mole calculations allow you to calculate how much substance is in a certain concentration of that compound. And when you've got the substance neutral at the bottom, you know that the number of moles of acid, i.e. the number of acid molecules there, is equal to the number of moles of base. So that's the other compound there. The number of molecules is physically equal, or you know that there's a ratio. So sometimes it's 1 molecule of acid for every 2 molecules of base. You know the exact ratio. You know that the ratio is correct because the solution has ended up being neither acidic nor basic there. So when that's the case, you know the number of moles. Number of moles is the only one that is interconvertible between different substances there, because the number of moles is physically the number of molecules in there. So there we go. Once you know that ratio, once you know that it's gone to neutral, you know that they are approximately equal. And so you would expect that you can therefore calculate the new concentration because the number of moles is equal to the concentration times the volume there. And again, this goes back to the workshop from earlier. So here are some base examples again, and I said that I'd mention about ammonia and how ammonia acts as a base. Well, if ammonia is a base, it is a proton acceptor. So if it's a proton acceptor, what that means is that it must somehow add onto its own structure a hydrogen atom that it doesn't have before. So here's ammonia. If you were to draw it out, you would figure all that out and you'd use VSEPR and dot cross diagrams to find out that ammonia has that lone pair of electrons there. So if it has a lone pair of electrons, then that means that it could possibly donate those electrons into a covalent bond. If a covalent bond is a shared pair of electrons, maybe it's possible for both of those electrons to come from one atom. And it is. This is called a dative covalent bond. So before we said that that wasn't right, and that was true. When we had atoms bonding together that were trying to complete their octets, yeah, that was absolutely fine. Now what we've got is two molecules that have completed their octets, but can still be associated nonetheless, and this is an ammonium. So here what we've got is the ammonia is donating its lone pair electrons to make this brand new NH bond. And in so doing, ammonia over here has basically gained a charge and become an ammonium ion. So notice that this positive charge doesn't disappear. If there is an imbalance between the number of protons and protons and electrons before a reaction, there still will be afterwards. Electrons and protons do not disappear in a reaction, they just rearrange. And so our ammonium ion, the NH4+, ends up also being positive. This is a dative covalent bond, so it's a covalent bond, but it's dative because they both come from one atom in there. And so we sometimes represent that with this little arrow structure here, or you can represent it like in the Lewis structures with two dots in between. But this is how ammonia can act as a base. It can accept a proton by donating its lone pair electrons, and things like water can also do that. So they can also act as bases. Anything with a lone pair of electrons tends to be able to donate them to a H+ ion, and thus they are also themselves bases. Now, this structure is 2D, so let's just remind ourselves about VSEPR for a second. So that would be 4 groups of electrons. It'd have that tetrahedral structure again, wouldn't it? And this takes us back to the wedges and hashes that we've sort of seen before. A wedge bond at the front, so that's this one here, represents atoms coming out towards us. So if I were to get my model back together, again, I think I showed you this earlier, but let's just look. So let's arrange this molecule. Let's say that those are flat in the plane there. So this is like a flat piece of paper here. There's an atom coming towards you there. That would be wedged. And then this atom coming away from you is hashed there. So you've got the wedge one and a hash one. And there's the molecule as a whole. Ooh, guess my fingers are a bit in the way, aren't they? But there you go. So it too is going to have that tetrahedral structure in there. And you can draw that as in a 3D representation like that. Okay, lovely. So let's have a look at this. I want you to have a look at this and just think about balancing this equation. So please pause and have a look, and let's think about it. Okay, so there are a few different ways to approach this. The first one might be to look at how many atoms are missing on the right-hand side, missing on the left that should be there from the right-hand side. So I might say, okay, well, I've got 2 oxygens, 2 hydrogens there. I've got 4 there, so I've got to at least have 2 hydrogens. Or you might just say, well, look at this salt. It's sodium sulfate. So it's got to be sulfuric acid, has got to be the suggested compound. But if we go through it a different way, you basically count up your hydrogens, so and all your other atoms. So we've got Na, S, O, and H on that side. And I'll do the same on the other side. We've got Na, S, O, and H on the other side. Draw a line there. So how many sodium atoms? I've got 2. How many sulfurs? Just the 1. This SO4 is 1 sulfur and 4 oxygens. So there's just the 1 there. How many oxygen atoms have I got? I've got 4 there. And I've got 2 lots of H2O. So 2 lots of a molecule that has 1 oxygen in is 6 oxygens in total. How many hydrogens have I got? I've got 2 lots of H2. So that's 2 2s are 4. So I've got 4 over there. Is that all correct? Looks like it's correct. It's quite often that the first time you do this, you're not all correct. So if I've done that, that's completely normal. Don't worry about it. But let's give it a go. Sodium. I've got 2 NaOHs, so I must have 2 sodiums here. Sulfur. I've got none at the moment. Okay, so I'm 0. How many oxygens have I got? I've got 2 lots of NaOH, so 2 molecules which contain 1 oxygen. So I've got 2 of those. And how many hydrogens have I got? I got 2 of those. So now I just look at the difference between the two. Okay, it doesn't contain Na because they're happy. It needs to have at least one S, so it's going to be something with an S in it, because at the moment on this side I've got 0 sulfurs, and on the right hand side I've got 1 sulfur. So it's got to have a sulfur. Oxygen, O2 on that side and O6 on the other means that this has got to be an O4. Okay, so this is kind of defining some stuff. And finally, hydrogens, well, I've got 4 on the right-hand side and only 2 on the left. So there must be 2 hydrogens as well, H2SO4. So that also confirms D as being correct. Though if you got C, that's fine. You just missed a hydrogen, which is totally normal. But I hope going through that helped you out. So do be aware that the big number here multiplies everything after it. Okay. So which of these ones are the salt here? So we've got A, B, and C. So which is the salt? Well, the salt is the one that's made of ionic compounds. And we saw earlier NH4 and Cl. Cl is going to be a negative ion and NH4 is going to be a positive ion. And we know that the NH4 can't attach to the Cl because we saw this. Well, let's just go back up to the structure. We saw that it's now complete. If we look at its dot cross diagram, that nitrogen can't bond to the chlorine anyway. None of the hydrogens can bond to the chlorine. So they must be separate ions then. And again, you do want to try and draw out the compound as best you can. So C must therefore be the salt. Which one is the base? Well, the base, again, pause and have a think. But the base is a proton acceptor. So what I'm looking for now is a species that has added hydrogen to itself. And I would say that's this, isn't it? NH3 makes NH4. So the ammonia must be the base. And another way to think about it is, well, HCl, the Cl has got rid of a H by the looks of it. So it must be the acid. And so that'll be the next question, won't it? Which is the acid? The HCl must be the acid. And that makes that the base, doesn't it? So B is the base. So tempted to... No, never mind. B is the base. Great. So let's try and do a mole calculation now. So these are not easy at all. So I'm going to let you pause and have a think, and then we'll do the mole calculation together. I'm going to draw it on this piece of paper. Okay, let's give it a go. So the question... Ooh, now, is there a way for me to pop the question in? Yes, let me just put this in here. Yes, that works. So I'm just going to pop that question in this window so that we can think about it together. And I'll pop it over here. There we go. All right. So my first step in doing these then is to write out the equation and make sure it's all balanced and everything. So I've got HCl plus NH3 makes NH4Cl. Then I write down what I know about everything. So I'm going to need a concentration and a volume for each thing to try and find a number of moles. So I'm going to write as much as I know about each thing. So now I'm reading the question and I see it says 20 mils of NH3. 20 mils, okay, that's a volume. So I'm going to put 20 mil is titrated to neutral against 30 mil of HCl. So that's 30 milliliters there. Hopefully that's clear. It's not completely obvious. 3. Okay, great. Oh, and it's also told me the concentration. So the concentration of something is how much substance, moles is the number of atoms, How much substance is in a certain volume? So that's 0.1 moles per decimeter cubed, and that's the HCl. Okay, great. So what's the question asking? What is the concentration of the NH3? So I'm trying to get to here. Always in these questions, it's about calculating the number of moles. So I'll have a quick look at these figures. Now, number of moles. If I just look at the units for a second, I'll notice that I've got mils and decimeters cubed. So I'm going to have to convert one into the other. A quick reminder, a decimeter... I should say a milliliter is a centimeter cubed. So that might make life easier. And for milliliters, that is also a centimeter cubed. So I would like you to know that 1 mil is 1 centimeter cubed, basically. So if that's a decimeter long, a decimeter is 10 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. So a decimeter is 10 centimeters. A decimeter cubed then is going to be 10 centimeters by 10 centimeters down. So we're thinking about a cube here. And it's going to be 10 wide as well, 10 centimeters. So that is 1,000 centimeters cubed then, is a decimeter cubed. Okay. So I'm just going to zoom in on that a little bit, make sure that it makes sense. Whoops. Like that. There we go. So I need to calculate the number of moles, but that means I need to change the volume into decimeters cubed. So I'm saying 1 decimeter cubed equals 1,000 centimeters cubed. So to convert this centimeters cubed into decimeters cubed, I need to divide by 1,000. Because it needs to get smaller, doesn't it? If it's currently in a small unit and it's going into a big unit, the value has to get smaller. So the number of the volume then is 30 over 1,000 decimeters cubed. And over here it's the same, 20 over 1,000 decimeters cubed. Okay, so we're getting a bit messy now. Let's get ourselves a new piece of paper. Hopefully I haven't written on too much. There we go. So far I know that the volume is 30 over 1,000 decimeters cubed and 20 over 1,000 decimeters cubed. To figure out my number of moles, which is in the unit of mole, I can just look at the unit analysis here. So I've got a value in moles, and I've got a value in, moles per decimeter cubed, and a value in decimeters cubed. So if I think about the unit analysis here, I've got mole per decimeter cubed. And remember, that can be written like that. So that is exactly the same as a mole per decimeter cubed, like that. So imagine if I took mole per decimeter cubed, and we just imagine that this is like algebra, and I times it by a value in decimeters cubed, well, A over B times B is A, isn't it? So that means that if I take these numbers, this number in decimeters cubed and this number in moles per decimeters cubed, 0.1 mole per decimeter cubed times 30 over 1,000 decimeters cubed, I'm going to end up with the correct number. So let's get a calculator on the go. Pew. So over here I'm doing 30 over 1,000 is 0.3 times 0.1 is even smaller. 0.003 moles. Okay, so here I'm saying in the titration, if I just pop back to the slides here, just go back up to that titration demo there. Oh, in fact, go all the way down to the titration demo. Ugh. Well, that was faff. If I go all the way back down to the titration demo here, what I'm saying is that I added that much of the acid, so that was where we're adding our 30 mils of the acid, and that has made the number of moles equal. So here what I'm saying is I have as many molecules of HCl, if I pop back to this, I have as many molecules of HCl as I do NH3. That's why it's ended up being neutral. They're supposed to balance each other, aren't they? So if that's the case, then that means that the number of moles of NH3 is equal to this number of moles of HCl. There. So that means I can calculate the concentration then. If the concentration is moles per decimeter cubed, then again, let's just think about the units that I've got. So now I'm thinking about ammonia here. Currently I've got a number of moles and I've got a volume of 20/1000 decimeters cubed. So I've got moles and decimeters cubed, and I want a concentration. What unit is the concentration in? Moles per decimeter cubed. Right, so I just need to divide one by the other then. Concentration is the value of moles, that's N, over the volume there that I've got, V. Okay, cool. So the very last bit then is this concentration here is, I should have used a much bigger piece of paper. Please excuse the fact that I'm using a different piece of paper. So the concentration of this is the number of moles, which is the same as the acid. So that's 0.003 mole. And I'm dividing that by the volume of the acid, which over here is 20/1000, 20/1000 decimeters cubed. Cool, so let's get our calculator back, and let's get our question back just to make sure that we're doing the right thing here. What is the concentration of the NH3 in solution? Well, I know that there are 0.03 moles of it, and I know that that is present in 0.020, so that's 20/1000 decimeters cubed, 0.15, I think. And the unit is moles per decimeter cubed. There. So concentration is 0.15 moles per decimeter cubed. Now, I realise that got very messy, but try to do it more organised than me. I still really do like to try and keep that structure where we've got N, C and V, N, C and V of every compound. You convert whatever you can into the number of moles, then swap between number of moles to switch between your compounds. And once you've done that, you are going to then convert your number of moles back up into whatever the value is that you want. Okay, hopefully that helped at least a little bit. So in there, what we talked about today is the H plus ion is called a proton. An acid donates protons. Bases are proton acceptors, so they remove protons from the solution. And we can use titration to find the concentration, basically by converting between moles and concentration, essentially. We're just using unit analysis to swap everything around. Okay, thanks for watching. I'll see you in the next lecture.